Here's our example. We have a park ranger driving his car. Here's the car. We'll say it's one of those Jeeps, since you're a ranger. There we go. So y'all like pictures? Sees a deer here. Here's my animal. There's the antler. Here we go. I wish the deer was looking at the car, but so the ranger was driving his car. He sees a deer. You know, deer froze in the headlight and doesn't move. The ranger is driving at a speed of 11.4 meters per second. Its initial velocity, 11.4 meters per second. Sees the deer, hits the brakes. The acceleration, now notice the acceleration in the book says is 3.8 meters per second squared. And if you write that, that's wrong. It should be a negative. Why? Because the car is going to slow down. So they're not going to tell you positive or negative. You got to read into it. If you're slowing down, that's a negative acceleration. If you're picking up speed, that's a positive acceleration. The deer happens to be 20 meters away from the car. The question is, does the ranger hit the deer? Does he stop before he hits the deer? And if yes, how far from the deer does he stop? Well, when the car stops, we're going to assume we're not going to kill that deer, poor animal there. Let's say the car stopped here. We'll see if it's before we hit the deer or not. When the car stops, what is your final velocity is? Your final velocity is 0. So how long is it going to take the car to stop? That's my question. How far? How far does the car travel, the truck, the car, travel before it stops? And if the answer is more than 20 meters, that deer is history. It's venison meat. I don't eat that. Ugh. If it's less than 20 meters, the deer is safe. So is there an equation? Here's my 4 equations. Is there an equation I can use here that will tell me what that distance is? If I number these 1, 2, 3, and 4. Which equation do you think will give me that answer? Can I use equation number 3 to give me the distance x? We don't know the time. Good, that's out. Can I use number 2? Well, that doesn't have distance in it. That's out. Can I use number 1? Not really. Why? You don't know the time. Can I use number 4? Possibly. Change in x, we'll call it. Delta x, the difference between the two x values. So what is my final velocity? 0 squared. What's my initial velocity? 11.4 squared. 2 times negative 3.8 times the change in x, the distance traveled. Let me get my calculator ready here. Clear everything? Okay, now let's take 11.4 and square it. 0 equals 129.96 minus 2 times 3.8, that's 7.6 delta x. If I bring this one to this side, change sign. What is delta x equal to? 129 positive, right? 17.1 meters. So it's going to take the car 17.1 meter to actually stop. The deer happens to be what? 20 meters away. Are we going to hit the deer? So how far from the deer are we going to stop? What's that distance?
2.9.
Yep. So you're going to stop 2.9 meters before you reach the deer. And while we're at it, can we figure out how long it took the car to stop time-wise? How long? Did the car travel before it stopped? How far did it go? We're looking for time here. So if I'm looking for time, I bring my equations back here. I know the final velocity. I know the initial velocity. I know the acceleration. Can I find the time? So equation 2. VI or VO is the same thing. 0 equals initial velocity 11.4. This will be minus 3.8 t. T equals 11.4. T equals what? Three seconds. Now, let's talk about distracted drivers. I'm one of them. I'm guilty just like the rest of us. When you look down at your phone, if that ranger happens to be looking at his phone or her phone, look down for 1 second and look up and see the deer. Because you were looking down, you drove for 1 second. Well, how far did you drive in 1 second? Your speed is what? 11.4 meters per second, right? So that 1 second, you didn't touch the brake because you weren't looking, you didn't see the deer. You already drove 11.4 miles. I mean meters, not miles. 11.4 meters. Add to it the 17 plus meters that you need. So how far did you go before you came to a complete stop? 11.4 plus the 17.1. You're going to stop at 28.5 meters. What happens?
You hit the deer.
You hit the deer. That's the part people don't realize when we're on the phone. Like if you look down for a second or two, or when you're an older driver, and I consider myself one of them. You know, I'm 60 plus, and my reaction is not as quick as somebody who's 18 years old. You see something, I can see it sometimes, especially when I'm driving for a while. I see something that takes me a while to sink in. Oh, I better hit the brakes now. My wife says, slow down. I go, oh yeah, you know. So your reaction, it might be like half a second slower. Well, half a second slower, I traveled already 6 meters. That deer, I hit that deer. That car is damaged now. The deer is dead. So really, that's where the problem comes in with distracted drivers. Is like You say, well, I've been driving for a while, I'm good. The law probably going to catch up to us one day, you know? You'll be looking down like you're not looking up, and I hope it's not some child running across the street, something like this, you know? Because our reaction time, that 1 second, doesn't seem far. Imagine if you're going now 40, 50 miles per hour. If you're going 50 miles per hour, 60 on the highway, 60 miles divided by 2.24, every second you travel 27 meters, almost 30 yards. So if the car in front of you stops and you're not looking, by the time you look up, you're on their tail. So don't text message and drive there. You know, I'll try to tell myself that too. Hopefully I remember that. Yeah. I'm not as bad actually. I try not to, but that's where really the problem comes in. Okay, let's try another example. If we can get another one. Ooh. Let's get the state police after you. Catching a speeder, somebody speeding here. So we have a road marked 25 miles per hour. That's down the street from you. And you decide you're going home. You're tired. We're going to put you in a sporty looking car. We'll give you a hot rod. A Volkswagen, one of those hot rod. You've seen them, or Subaru, the hot rod. I've seen some of the young ones driving. You're driving 40 miles per hour. Your initial velocity. So the road is marked 25 miles per hour. The street says speed limit 25 miles per hour. You're going 40. The 40 miles per hour is roughly about 17.9 meters per second. So if you want to convert that to meters per second, it's about 17.9. You divide it by 2.24. We have that conversion from chapter 1 or chapter 0. 40 divided by 2.24, 17.9. If you can't see it, I'll move it. There we go. So you're driving here 40 miles per hour, cruising there. Well, you didn't see that, but there's a cruiser right here. State police, well, trooper. Let's put a light on top of their car. There's the light. Just you go by them, you're not paying attention. They flicker the lights. They saw you speeding. So this guy is actually not moving. What's the initial velocity of the police? That's 0. So what's going to happen as you're going, you're going to be down here, and the police still going to be right here. But he is really stepping on the gas, catching up to you, coming after you. Got to put some drivers here. Eventually now the police is going to catch up to you. Right here, there's you. And there's the police right next to you. Go and pull over. So you travel really the same distance in that story there. Now let's assume this driver kept the speed constant. So constant speed. Didn't step on the gas because you busted. Pretend it's not you. Like, let me just leave the speed alone. I don't want to hit the brakes. They'll know it's me speeding. Let me just keep going at constant speed. Or maybe didn't even see the police at all. Now the cruiser coming at you with an acceleration here of 4.51 meters per second squared. The first question, how much time does it take for the police car to catch the speeder? How much time, bless you, it take the police to catch the speeder. Second part, how far did they travel? Assuming they're going to stop at the same, like this, to start at the same spot, right there. How far did they travel, distance? And let's ask you the last question. How fast the police car was traveling when it catches the speeder? So we have three questions.
Is the they the police car or the person speeding?
Which one?
And B is how far did they travel? Is that the police car? Or the
Both, because we're looking at them. You go from this point to that point. Should be the same when they catch up to you. So that distance will be the same for both of them. That's the assumption we're making. I'm looking from this point, how long it took the police to catch up to you, how far they travel from that point to this point. Yeah. Like a two-lane street, and the one was in the left lane, one was in the right lane. So it's not like we could say, well, if he pulls behind me, then it's not the same distance. So assume it's a two-lane, and the police pulls right next to you. So let's break it down to two parts here. Here is the speeder, and there is the police. For the speeder, what we know is what? Constant velocity. And that's equal to what? 17.9 meters per second. If your velocity is constant, what does that mean about your acceleration? 0. What does that mean about your final velocity and your initial velocity? They are equal. It's equal to your average velocity. It's the same. It's constant speed. It's 17.9 meters per second. Notice if your acceleration is 0, if you look at that sheet, if A is 0, this piece is gone. It says your final velocity is the same as the initial velocity. And if your acceleration is 0, that says the final velocity square equals the initial velocity square. That equation is gone. If the acceleration is 0, this piece is 0, it says your distance equals what? Since I make this the initial always 0, so I'm going to mark the distance like this is the 0 mark. It's going to be 0 plus the velocity times time. So there's only really one equation when you have constant velocity, and that's x equals the distance equals the initial velocity times the time. That's it. There's only one. These four equations become one single equation when your acceleration is 0. And I know my initial velocity is 17.9, so x equals 17.9 times t. But I don't know what that question is. Time. How much time? That's my question, so I can't tell you. And how far, that's x. I can't tell you. I got two unknowns. Let's look at the police car. What's the initial velocity? 0. What is the acceleration? 4.51. What's the time? Unknown. What's the final velocity? Unknown. What's the distance traveled? Unknown. That's all we know. So let's see if I put my equations up here, if I can find something useful here. Here's my equations. I know the distance traveled by both cars is the same. I know the time is the same. It has to be the same. So the time and the distance have to be the same for both of them. So I got to find an equation here that has x and t in it, because the time is the same and x is the same. So I got to look at my equation. Is there an equation that has x and t in it? Well, I could use this, but I don't know what the average velocity is, right? For the speed, that car, the police. That doesn't help me. This doesn't have x in it. But this does. So let me look at that equation for this for the police. Again, we're still talking about the police here. What about if I use this equation? X equals x sub 0 plus v0t plus 1/2 at squared. The distance traveled by the police is equal to, the initial value is 0. What was the initial velocity of the police car? 0 times t plus 1/2 times the acceleration, which is what? 4.51 times t squared. X equals 2.505, is it? And the equation here, x equals 17.9 t. So this is for the speeder.
It's actually 2.255.
255, thank you.
2.255, yeah.
You're right, yeah, because that's a 5, yeah. And what do we know about these two distances? Here's my picture. What's that distance from here to there in relation to the distance from here to there? They're equal. So set these two equations equal to each other. You have a quadratic equation. Bring everything to one side. Minus 17.9 t. I don't know why I put parentheses there, because I know where my brain is thinking about the next step, is equal to 0. How do you solve a quadratic equation? What do you do? Well, we can factor a t out first. You multiplying two things, your answer is 0. That means one possible way if t equals to 0. And you're right, at t equals to 0, the distance is the same. That's right here. The other value is down here. So the other value, when 2.255 t minus 17.9 is equal to 0. Or 2.255 t is equal to 17.9, t will have to be what? What is 17.9 divided by 2.255? It took them 7.94 seconds for the police to catch up to the speeder. Almost 8 seconds. That's part A. Part B is the distance. How far did it go? I can use either equation. I can say x equals 17.9 times t. $142 meters. In part C, it says, how fast was the police going? How far was the police going when they actually caught up to the speeder? That's the velocity we're looking for. So I gotta look for a different equation. I know the initial velocity. I know the acceleration. I know the time. Can I find the final speed for the police car? So that's part C here. V equals V0 plus AT. The acceleration, what was the acceleration? 4.5? Was it 4.5? 1, yep. And what was the time? 7.94. $35.8 meters per second. Multiplied by 2.24. Cruiser's going 80 miles an hour. The state police. It's 25 mile per hour zone. You're going 40, they're going 80.
And it's okay.
Yep, they're gonna get you. If he's going 80 miles per hour, giving you a ticket, trust me, you're not getting away free there.